Welcome to the second video in a series of 6 on solving systems of linear equations in 3 variables. In this video, we'll cover the technique of substitution. Before you watch this video, a brief note of caution. This is called a 2-variable system in 2 equations. And this video that you're about to watch presumes that you have the algebra skills to solve this. I recommend hitting pause right now, solving this system for x and y before continuing. You should have discovered that the solution is 5, 7. If this is not a skill that you possess, please go back and watch the video called Systems of Linear Equations in 2 Variables, because in video 2, in this next video that we're starting, no algebra will be shown. It will just be assumed that you have this skill, because this skill is a small part of the bigger skill that we're building here, which is solving 3 equations in 3 variables. With that caution in mind, let's look at our first example, which turns out to be, as we'll discover, a system of equations that has a single solution. Okay, so how do we go about finding this solution? Well, remember what we're looking for. We're looking for values of x, y, and z, a single-ordered triple that will satisfy all 3 equations. One technique of finding that is called substitution. In substitution, you solve any equation for any variable. Now, what do I mean by that? I mean, we have 3 equations, each has an x, y, and z in them. There are literally 9 letters in this problem. And I pick one of those 9 letters, and I solve that equation for that letter. Now, while you technically have 9 choices, I'm going to recommend solving for a variable that has a 1 or a negative 1 coefficient, as you've seen me indicate here. And I recommend actually solving for a variable that has a positive 1 coefficient. It just makes the algebra easier. Could I solve for the x in the first equation with a negative 2 in front of it? Sure, if I wanted messy algebra to follow, sure, I could do that. But I'm going to recommend solving for one of these variables, and I just arbitrarily picked one of the variables that had a positive 1 coefficient. So I'm going to solve for y in the first equation. I'm going to take that equation here, and I'm going to solve it for y. When I say solve for y, I don't mean to find out y equals number. I mean we're going to isolate y and solve for y in terms of x and z. So to isolate the y, I'm going to add 2x to both sides. That will cancel my negative 2x. And I'm also going to subtract 4z from both sides. That will cancel my positive 4z. And here's the result of me having solved for y. So now that I've completed this, I've solved any equation for any variable. It turns out I solved the first equation for y, but it doesn't matter which variable you solve for. You then substitute that result into the other 2 equations. Now the phrase other 2 is really important here. Other 2 means the 2 that I didn't just use. After all, if we have 3 equations and we solve one of them for one variable, there's going to be 2 I haven't used yet. So I take those 2 as of now unused equations, and I'm going to substitute the previous result. Here's what I mean by that. We just discovered that y is 13 plus 2x minus 4z. That means, here's the clever substitution, I can replace the y's in my unused equation with those quantities. This is a big concept, and it's very useful in mathematics. You may want to pause and make sure that you see what just happened before proceeding. Okay. Now, what I do what I tend to do next and like to do is I like to simplify these messy equations. Now, it turns out this equation here, after a lot of ugly algebra, simplifies to this. If you're the kind of student who likes to see every single number worked out, then you're going to want to hit pause and watch my algebra here. Okay, rewind if you missed that. Let's move on. This equation here, it turns out, simplifies to this after lots of messy algebra. If you'd like to hit pause and examine the messy algebra, here it is. Okay, now after doing all of this algebraic manipulation, let's examine what we have here. We now have created a system of two variables in two equations. In other words, I've reduced the original problem, notice the problem at the top, I've reduced three equations in three variables down to, notice the thing at the bottom, two equations and two variables. Now this video presumes that you have the math skills to go from there to here without me showing any algebra. If you'd like to hit pause and do the algebra yourself, that may not be a bad idea. Now that we've discovered what x and z are, all we have to do is substitute that result, the one from the two variable system we created, into any of the problems on this screen. Now, what's the remaining variable we haven't solved for? Well, it's y, of course. So I probably would be well advised to pick an equation with a y in it. Now, you can pick any equation you want. I typically use the original equation, and although it's not mandatory, and there are other ways to do it, but I'm going to use this equation here at the top, the second of the original equations. Take that equation, and I'm going to substitute x equals 1 and z equals 2 into it. And once you've done this, you have a very simple equation you can solve for y. There are the details. And now that we've solved for y, having originally solved for x and z, we now have our single solution. And that single solution is the order triple, -1, 3, 2. Now, if you watched video 1, you may recall that there are three types of results that we can get when solving a system of equations in three variables. One is a single solution, as we see here, and the other two possibilities you may recall are no solution or infinitely many solutions. So how do we know if this single solution is the only solution to this system of equations? Well, it turns out if you do the algebra and you only end up with a single solution, then it's fair to deduce that that is the only solution to this system of equations. So this is not a no solution type, nor is it an infinitely many solutions type. Those we're going to see in our next two examples. Suppose we were to take this same problem that had no solution and make one minor change. Suppose I were to change this 12 into a -3. Now this is a completely different number. But it turns out instead of having no solution, this system of equations is going to turn out to have infinitely many solutions. By the way, I'm not suggesting that if you randomly change one number that you will always get this result. I specifically did all the work behind the scenes to know that. But what I'm pointing out is that we should now take a look at a system of equations that has infinitely many solutions. Now you wouldn't know it to start. All systems of equations look roughly the same. And so when you're presented with one and asked to solve, you don't know if there's going to be a single solution or no solution or infinitely many solutions. So you set about solving them in the same way either way, you discover in the process. We will discover that this system has infinitely many solutions. Pretend we didn't know that, and let's go about the business of solving. So we're going to solve any equation for any variable. Again, I'm going to solve this equation for x, just like I did on the almost identical problem a minute ago. And just like I did before, I'm going to take the two unused equations. I'm going to take the fact that I've solved for x, substitute that into the two unused equations, and do all the same ugly algebra that we did before. There's fundamentally nothing that different about this problem. I changed one number and it changed a little bit of the algebra, but the process is the same. But the outcome is dramatically different. When we go to solve this system of equations, using the techniques you've learned in prior classes or by watching my prior video, I would choose the addition method here, you're going to end up with a statement 0 equals 0. In mathematics, this is called an identity, a statement that's always true. And it doesn't indicate that 0 is the answer to the problem or even that there's no answer. 0 equals 0 is an identity, an always true statement. What that indicates, you may recall from previous classes or my videos, is that when you get an identity like 0 equals 0 or 5 equals 5 or 2 equals 2, that's an indication that the system you're trying to solve has infinitely many solutions. Now, if that two-variable system in y and z has infinitely many solutions, it stands to reason that the original system we're trying to solve at the top of the screen also has infinitely many solutions. And that completes the second video in this series.